Good afternoon, everyone. I'd like to thank the organizer, Brian, Jan, Max, for inviting me to give a talk today. I've had a wonderful time, learned a lot of things about aging. So today I'm going to give a more computational perspective to understand and describe aging. So you know, in life we go through the different stages, right? So from birth, growth, then you become an adult, and then you think about, you know, how fit you are. The concept of what is robust, and eventually you will age and die, right? So I will try to describe all these things from a computational point of view. So also, so when you think about like fitness, you think of like how to maintain. So for most of us, we are like adults, how to maintain or even to repair our body, right? So how do you couch these terms from a computational complex system perspective? Okay, so my talk is basically going to describe all these phases or terminology. Okay, so there's this tree of life where this paper, a Nature paper, talks about the different mortality, fertility, survivorship. So we've seen a lot in this conference as well, particularly the use of survivorship. You know, it follows this shape. So later on, I'll describe a paper that talks about this kind of things. Okay, so I'm more like a physics background, but if we read papers, then you see, particularly from the biology side, how they describe aging, right? So typically they think about decline in function, in health, and lifespan. So for example, in this Nature Aging paper, things like, you know, you can have biomarkers like the heart rate variability. So what you see here is that young individuals, they have high complexity in the data signal, but over time, when you become old, the variability decreases, right? And there are also other markers that you can use to describe this kind of eventual homeostasis. So basically, these are concepts that I hope to basically explain to you using a computational model later. Okay, so basically the framework that I want to use is basically complex networks. And why is it relevant? So you can see the approach that different fields have used in the past. So for example, in ecology, in the past, what people have been using is more like a top-down, bottom-up thinking. So where you're thinking like, okay, you have this particular pathway and you can describe a particular phenomenon. So what we know is that nature is not so simplistic, right? So there are many factors involved, and it's actually a multi-factor, multi-pathway kind of interactive picture, particularly non-linear, right? So it's very rich, and you can expect a lot of interesting things. For example, in mathematics, you may describe things like bifurcation. That would correspond in biology to something like mutation, right? So it's something very different. So using this example where you see that, you know, let's say if you're interested in seal hunting, you may want to do a particular thing, let's say in order to control or improve the amount of caught fish. And similarly, if you use this thinking and you approach to aging biology, then you look at things like oxidative stress. Then you could say, you know, look at different processes, and now you can see if you apply a framework like this where it's multi-pathway and multifaceted, then a very rich picture emerged, right? So there's this concept of, in physics, or particularly statistical physics, of emergent states, emergent properties, or even like phase transition. Can we put it into this kind of context? Okay, so how can we use network science to model complex systems like this? Okay, so let me start with a simple example. So in complex system, the foundation is basically the concept of a graph, right? So in the graph, you have these nodes, and then you have these links. So basically, the nodes and links can have different meanings depending on the setting. So for example, if you think of a Hollywood actor network, then the nodes could be like individuals, and then the movies could be like collaborations. Okay, so if you put it into biology, then for example, you could have a protein-protein kind of network, and then you look at this kind of interactome, right? So for example, in this case, the nodes could be like proteins, and then the links will be some kind of links between the different kind of proteins, and from there you hope to discover patterns or clusters within this kind of networks to see if you know how the different diseases are correlated with the different kind of proteins in our body, for example. Okay. Okay, so we know that complex network has been very successful. And the most famous example is probably this kind of epidemic spreading. So for example, it has been used to study things like SARS spreading. So here you can see it originated in Hong Kong, and then over time it spread it to the rest of the world. And then you can basically think of it as a complex network. And then in this case, the nodes are individuals, and the links are basically people who have interacted with the patient, right? So you can see if you reorientate this very huge complex network, you can see this propagation of infection across this complex network, right? So it becomes kind of like a wave that's spreading. So you can see that there's a lot of richness that can be discovered through this kind of framework. So let me go on to the first concept that I mentioned in the first slide, which is how can you describe growth in a complex network, right? So one of the most famous example is this Barabasi-Albert model, the BA model, where basically it showed, the authors were able to show that they are able to get this kind of scale-free network. Okay, as you can see, it's really two simple mechanisms. At each time step, you add a node to your complex network, and then this node has some kind of preferential attachment. So basically, nodes with more attachment is more likely to gain a new node that is attached to it. And then what you see is that you get this kind of scale-free in the sense that there is no characteristic size scale or time scale to it. Okay, so you get a power law, essentially. So the idea of a power law is that there's no scale to the problem, so it's scale-free. Okay, and this kind of scale-free network exists a lot in biology, from yeast network and so on. You'll find that this kind of patterns in terms of the degrees. So here is the number of degrees of the nodes. So basically what you find is that the degree scales as k to some negative exponent. So actually my field of work is more in this area of growth. So in the past I've used this kind of graph structure to describe things like growth in avian eggs. So for example, here you can see you have a circular kind of graph, and then you see differential growth, and eventually you can generate different shapes that you see in avian eggs. And then more recently in my group, we have been thinking about how to describe self-assembly and swarming of honeybees. So you can see here is like some screenshots of honeybees swarming. So this happens when a bee colony wants to reproduce. So basically, a queen bee will migrate and bring a lot of workers bees, and then they'll form something like this temporarily before they find a permanent site to live in. So you can see we are able to use this kind of complex network to understand the force chain that exists between different bees in a dynamical process. So and basically to understand the interaction, the connectivity that exists within this kind of bee structures. Okay, so this is the concept of growth. So an important concept and the theme of this conference is aging. So how would you describe aging using complex network? Okay, so basically we can understand aging as the process of damage accumulation with time. So in the context of complex network, so let's try to understand it from a real example, right? So for example, here we have a blackout picture, and then you can see that there was this big blackout in North America in 2003. So basically, these are the lights, and then you can see America became very dark right after the blackout. So why did it happen? So basically, you can understand this kind of power grid as a complex network, and the reason why blackout became large scale is that there's the failure of hubs. Hubs are nodes with a lot of connectivity. So basically, once you have this kind of hubs failing, then the system cannot sustain itself and then eventually fails, right? So you can see that this can be applied to a lot of biological systems, right? Because biological systems are multicellular entities, right? So the question is, if one or two cells fail, it's fine, right? But if you have a cascade of failures, then that organ will fail, right? So you can see that these kind of concepts can be applied and studied using the framework of complex network. Okay, so in terms of the application of aging, there are two ways you can think of like failure. One is you just remove a node from your complex system, right? If you remove one node, then it disappears. And the other is basically you can remove a link, right? So these are two mechanisms that you can mimic failure. Okay? So this problem has been studied by various groups, particularly by Barabasi's group in, so basically, and also the group in, by Heflin. So you can see that it depends on the so-called how connected the network is. So basically the topology of the network is very important when you think about failure. And what you see is that for a network that is very, very connected, the number of nodes you need to remove before it fails will depend on this exponent, right? So in this example, you can see the more connected, the larger the exponent, the sharper is this transition. Okay, and you can also see the difference between removing links versus removing nodes. Okay, so in both cases, you can see this sharp transition where the largest clusters basically leads to a catastrophic failure in system-wide. Another way to view about this kind of failure in the context of complex network is as follows. If you think of the diameter of a complex network, which is the shortest path between any two nodes in the system. So there's a difference between attack and failure. So in an attack, what you do is that you target hubs, which are nodes with very high degree of freedom. When you talk, on the other hand, for failure, you're really just removing nodes at random. So the nodes could be something unimportant, whereas attacks in the context of complex networks specifically refers to removing hubs. Okay, so there's a very different behavior. So you can see that if you're attacking hubs, the diameter of the network increases very quickly. Whereas if you are just removing nodes, the effect is basically very small if the fraction of nodes being removed is small. Okay, so another concept is that I talk about is this attack thing. So here's another view of it. So what you'll find is that you get a curve that looks like this mortality curve that we saw today, right? In this conference, right? So basically, you can see that this kind of framework will allow us to study things like survivability. Okay. So another concept that I mentioned in my first slide is this concept of robustness. Okay. So basically, how can we enhance a network robustness? So here, if you think about it, one way that we can modify a network is just by changing its topology, right? So you can see that by adding more links to a complex network, you can change the reaction to how you will respond to failure or attacks. Okay, so if you can then apply this concept to study aging, right? Because this connectivity, if you think in terms of like, let's say a protein network, basically it could be that, you know, there are more pathways, or, you know, if let's say if one of the protein is missing, then you need to provide an alternative pathway, right? So that kind of reasoning in order to make something more robust. Okay. So another concept that is important to understand aging is in terms of how can you control the states of a complex network. So for example, you know, in this case, the states, which are some value that the node takes, can be either a real number or something binary like 0 and 1, right? So the idea is that can you control and move the states to something that you want? So this problem was studied again by Barabasi's group in 2011. So for simplicity, they actually use a linear model. Okay, so again, this is a big simplification because we know that in nature things are nonlinear. Okay, so actually this problem hasn't been solved like 15 years from then, right? So, but what they showed is that actually if you are considering linear dynamics on a complex network, then it turns out that you can drive any nodes you desire to the final desired state. So this problem is doable. It just depends on how much energy you input to the system. Okay, so there are other papers like target control, which means that you only target a few selected nodes, subset of the nodes, where you want to drive the system to some particular state. So in my group, we have also done a bit of work in terms of how to do the optimization and as well as the energy scaling in this kind of settings. So again, this is, in some sense, we are kind of overstating it because this is a linear model, right? So this is really a big simplification. So I guess, if you really want to model nature, particularly aging, then somehow you need to improve this to make this a kind of nonlinear kind of dynamics. Then you will get even more interesting behavior. Okay, so now that I've described all these different facets that we can use complex network to describe, so what if you put it in all together in order to study aging, right? So this was done in a recent paper in Professor Mahadevan's group in Harvard. So what they did was they basically used these kind of concepts like node removal. So basically a node can fail, okay, with certain probability, and then you can repair the node with certain probability. And there are two ways the node can fail, either as a single entity or if enough neighbors fail. So if the number of neighbors who fail exceed a certain threshold, the node will also die. And they have a very simple kind of state that each node can be assigned. It's binary, either 0 and 1. And they define a kind of vitality called network vitality, which is basically the sum of all these binary variables, right? And you can see that this is actually equivalent to survival rate, right? We saw in many talks today. So basically, this gives you the probability of survival, if you think about it. So in their paper, they basically say that the system will fail if this exceeds, falls below a certain threshold that they set arbitrarily to 0.1. Okay, and what do they find? So they found was that it obeys this kind of mortality curve. So it goes from 1 to 0, and it has this characteristic fall off. Okay, so then the question is, how does the repair comes in? So you can see that there are different ways you can, if you repair enough, you can actually extend the mortality curve, right? So it actually becomes harder to fail, okay? And again, this is similar to this kind of survival rate that we saw in this talk, in this conference. Okay, so then in the paper, you can, they describe a simple mean field theory where you can solve this to make certain predictions. And then they also considered different ways to think of like repairing, right? So you can think of like in terms of what I showed on the first slide, repair can come into like rest and recuperation, right? So macroscopically, but in this kind of complex system, it's basically in terms of, how much energy you want to put in, right? Or how probable is it to repair a node, right? So they use a very simple cost setting. So basically you have some cost function over the time of the simulation, and it's discounted by some parameter. And it's really a linear cost function because in this case, the repair cost is always positive. So, in physics, we usually use a quadratic kind of dispersion, but because of it's always positive, so a linear system will work. And then there's some kind of mortality rate, right? Okay, so there's all this kind of interesting prediction on how much energy you want to put into repair and what is the optimal amount of control. So I remember Maha told me that he has this thinking that humans only need to exercise 20 minutes a day to increase longevity. So I don't know if it's like an urban legend or not, but it's kind of similar to this concept of repair. Okay, so let's go to the last slide. So I would like to talk about how you can use this to study evolution. So basically, there's this paper from Sanjay Jain's group that talks about autocatalytic sets. So the idea is that using this kind of directed graph and with a certain kind of very simple dynamical system with some simple rules. So basically, you have some kind of Darwinian rules where you have this survival of the fittest, and then basically what they show is that diversity actually increased the survivability rate of a collection of entities. So for example, if you think of this as a multicellular kind of network, then basically the idea is that if you have a larger set, it actually delays crashes. So what they found in their simulation was that you get all these kind of crashes if your system is small, but actually if your system becomes large, you actually can live longer. So this kind of agrees with our intuition on biodiversity that exists in nature. Okay, so this brings me to the end of the talk. Thank you very much.
Thanks for the great talk and introduction to complex systems. In your networks, in the networks you presented today, you always think of decline in function as loss of nodes or hubs, but it seems to me that when you think about the biology, you also have gains of function, and I just wonder how it works in a formalization of networks like this. Is it because of the inverse weights of some of the links or something like that? Because you can get dysfunction and decline through gains.
Yeah, thanks for the question. So I think it depends on how you define function, right? So usually in physics, we think of this kind of observable more like an emergent property, right? So I would say that, if you want to use a complex network kind of setting, then you need to basically look at what are possible emergent states, what are the different kind of phases, and then what you can get out from it, right? So if I've seen a lot of work from dynamical system people, then they will talk about like either chaotic states or like synchronized states, right? So I think those would correspond to functions in biology, right? So if you have different kind of synchronization, that could be understood as some kind of biological functions. Yeah. So at least that's my take on it. Thanks.
Okay, this is really interesting for me. So based on the complexity of aging network, so when you control duration of repair or amplitude of repair, how this kind of complex network respond? So are they tightly correlate with their complexity or their strength of repair and then amplitude duration?
Yeah, good point. So I guess, it's the amount of energy you want to invest in, right? So, so I think it differs from different systems, and I think this problem hasn't been looked at very thoroughly. So like what is the optimal amount of repair that you should invest, right? So it's kind of like humans, right? How much you need to exercise per day, right? So it's that kind of questions. So I don't think there's an answer right now. So I mean, in that particular paper I showed, they have certain results, but it's not general rules. So I don't think we don't have a general principle on how much repair you need. It's just that the intuition is that you need repair, right? But I think the answer is still somewhere out there.
Okay, in the interest of time, we'll have one last question from Brian.
Okay. So you showed that by using equations with breakdown of nodes or edges and then some repair function that you can alter survival curves. It's, a lot of thought right now in humans is that a lot of these interventions aren't going to push everything out. It's not a scaling effect, but it's going to be a squaring effect. So on the survival curve, so median lifespan will go up but not maximum. So is it possible to alter the curves in those ways using modeling in the way you're doing it?
So I think both can be changed, if I'm not mistaken. So the steepness as well as the mean value in which it decays. So those can be tweaked in the model. Yeah, so it's possible. So the answer to your question is, I think it's possible to do in terms of simulations. Yeah. So whether you believe in it, like how much realism there is, it's a matter of interpretation, right?
No, but it might be comparing the differences you have to make to get those two different events to happen and what it might mean for the models.
Yeah, so I don't have a quick answer right now. So I think it's really model dependent, yeah. But it can be tuned. Yeah. Yep. Thank you.
Okay, thank you very much, Professor Yong.